In this video I'll show you how to simulate a powder pattern and compare it to observed patterns. Open USCL and then open the ShellX folder. In the ShellX folder there's a subfolder BUDWEC. Open the BUDWEC job and then look in the folder. Open the folder. And if you look at the folder, you'll see there are 4 files present. The ShellX file, a P4P file, and 2 XY reflection files from a diffractometer. Now, most diffractometers can produce XY files. These XY files are simple, space-delimited columns of Bragg angle and intensity. That's all. They're very simple, and you should be able to get those files from any powder diffractometer. Now, to calculate the powder pattern, it's very simple from a ShellX file. You just click the powder pattern icon or toolbar button, and the defaults are usually OK. And the powder pattern is calculated. Now, in this case, we'll label 4 of the peaks. So, select peaks, and we're just going to label 4 to save time. The 4 strongest peaks are labelled, and when you have labelled peaks, you can calculate the indices for these peaks. Now the program looks to see if there's a reflection near the calculated positions, and you can see in each case it automatically picks the strongest peak nearest the value of the marked peak. This usually is OK. You can default on this normally. And so when we've done this, the peaks are now have their HKL values calculated. To observe those, we need to go to the options and switch the labels to HKL labels. We see the peak close to 17 is the bar 402 peak. We'll come back to that in a few minutes. Now we can easily convert those XY files that we have to files that USCL can read using the powder display function. So we run the powder utilities function first, and there we see we can convert up to 250 XY files to the ING format that USCL uses. This is very easy to do. You can default on all the options. And then the program runs very quickly and the files are written. Now we can redisplay the pattern we just calculated, and we can compare this to the patterns that were obtained by reflection mode and transmission mode. Reflection mode is the more common. We look at it first. In reflection mode, one peak dominates the pattern. We can clear the labels which are no longer relevant to this pattern. So we can see this peak dominates, and it's the one we label bar 402. Now we can remove this and compare it to the transmission mode spectrum quite easily by just using reset to go back and compare, and this time pick the transmission mode on _T, and we see that more of the peaks are observed in the transmission mode than in reflection mode. Now we can try to understand this if we examine the shape of the crystal. Now to examine the shape of the crystal, we run job and look for Ritnos. We can see Ritnos program does crystal morphology, but it requires files written by Ortex, so we just run Ortex and close it and run it again, and you can see this time the program starts without problem. Now one of the options is P4P crystal. So if we ask it to compute a crystal picture or shape from the P4P file, we pick the P4P file, it generates crystal shape, and we just pick the only crystal shape that's there, and this is now displayed. Now the disjointed nature of the outline disappears if you go in and out of setup. If we go into setup and click Face Labels, we see that the crystal faces are all labelled. Now there's a lot of labels, but if you move it around, you can notice that all the side faces along the elongated crystal have 0K index. That means that they all meet the B-axis at infinity. So the extended growth is in the B direction. Now we can see this more clearly if we superpose this crystal shape on the unit cell and the crystal packing that we can use from the ShellX file. So if we just close this and close Ritnos and run Ortex to generate a picture, we can pack it if we want, but we don't need to. If we run the OpenGL, we have what we had in Ortex. Now we can add to this, as I said, the unit cell, but also the crystal shape. And when we do that, we are asked to pick the shape we want to use, and it's the one we just generated. And now we can see that the extended growth direction is the B-axis. You can see that the red A-axis is along there, and the blue C-axis is there. The B-axis is the short one. So the extended growth is along the short axis. Now the reason for preferred orientation is this elongated crystal shape. If we turn around the crystal so that it's lying down, we have the crystal orientated the way it most likely would arise in a flat plate reflection mode geometry setup. Now we can examine this, and we can go further in a minute, but we can stack the results if you have software that can stack XY patterns. If you don't have the expensive Expert Pro package or something similar, you can use this free software from Jeremy Sanders. Now in X-ray powder diffraction, transmission mode has the beam going through the sample, and then the diffracted X-rays are collected on the detector. The sample is held between polymer windows, and the beam goes through the whole sample, not just the surfaces of the sample. In the reflection mode, it's the surface of the sample that's giving rise to most of the diffracted pattern on the detector. And this is the reason why the sample top in the pressed flat sample holder will tend to have the crystals lying down, and reflections which are parallel to the B-axis are enhanced, and in this case the bar 402 dominates.